Okay, I want to talk about the entropy changes associated with an isothermal reversible expansion. We have a system with its surroundings, so it's an isolated one. And so since it's isolated, we know that anything that happens from the system is going to go into those surroundings. So anything that goes into the surroundings has to come from the system, and it's not coming from anything on the outside. Okay, so we have an isothermal reversible expansion, and I want to know what is the entropy change associated with that. So delta S of my system is equal to what? Well, I know that I have, and my system is going to change from an initial state to a final state. So I know that from my initial to my final state, I'm going to have dq reversible per temperature. Okay, but because I'm likening this to an infinitesimal change, I'm wanting to say that this, or not necessarily an infinitesimal change, but I know that if I were to take the integral that would require it to be the path integral, that would give me q reversible over t. Notice how it's not a delta q, it's just a q reversible over t. Okay, I also know that this is an isothermal reversible expansion. Isothermal, so delta U, which is equal to CV delta T, is going to be 0 because delta T is equal to 0, which means by first law, delta U is equal to Q plus W, but because delta U is equal to 0, Q is equal to minus W, which then means that my delta S is equal to minus W per T. And I know, work reversible. And I know that work reversible is equal to minus, I believe I have a minus PdV here, divided by temperature. But then, because I have a dV, I want to take the integral and I want to see through the process, how does that dV change? But because my pressure is following a reversible process, that means that I'm going to have delta S is equal to, I'm going to go ahead and make that a positive integral. I'm going to change this to nRT over V dV, which gives me nRT log VF over VI. All right, so this is my delta S associated with the reversible expansion of, so the reversible isothermal expansion. Cool. Okay, but that's just delta S of my system. Okay. Now, if I want to know what is then my delta S of my surroundings, how would I find that? Okay, so I know that I have delta S of my universe is equal to delta S system plus delta S surroundings, but I'm not gaining anything from my delta S of the universe because it's a reversible isolated system. This is going to equal 0. So anything that leaves the system is going to go into the surroundings, which means that my delta S of the surroundings is going to equal a negative nRT log VF over VI, such that if I were to add them together, I'd get delta S of the universe is equal to 0, or delta S total is equal to 0 for reversible process. What about an irreversible process? So one way to set up the idea for an irreversible process is to think about free expansion. So if I have P equals some number, so I have a positive pressure and I have P equals 0. So this gas, say, is going to expand into this surroundings area, but it's still in an isolated container. So this is going to be free expansion. Whoops. Okay, so we've got free expansion. Which means that the Q of the system is still going to be the work. So it's still isothermal. So delta U is still equal to 0. So Q of the system is going to equal minus work done by the system. Okay, because anything that leaves the system, so any heat that flows is going to come from the work associated with it. Or likewise, anything that you gain the work is going to originate from the heat. So the Q system is still the work associated with the expansion, but it's not having to put anything into that expansion. Okay, so another way to say that is the surroundings gain 0 work from the expansion. And that's because, so delta S of the surroundings is going to be 0. Again, because it's not having to push against anything. If you think about it like Newton's third law, so any force is going to have an equal and opposite force coming this way. Because there's nothing there, the surroundings isn't gaining anything. So because it doesn't gain any work from the system, the delta S is going to be 0. But likewise, or not likewise at all, but there's still work associated with the actual expansion. And so it's just not gained from the surroundings, but it is lost by the system. So delta S of my system is still going to be, and make sure that I get the sign right. So is equal to Q over T, and that's going to be minus W over T, again, because isothermal expansion, first law, delta U equals 0. And so then from this is equal to 1 over T integral, this becomes minus P dV. So there's the negative, and then I work as minus P dV. And so that gives me a positive value, which means I've got integral nRT over T dV with a V. In the denominator, my T's cancel. So that leaves me with nR log VF over VI. Okay, and so this is going to be a positive value greater than 0. So not delta S of the surroundings equal to 0, but this is going to be a positive number. So N and R, both positive, log, that ratio is going to be positive. You're not going to get a negative value from the logarithm. And so that establishes that you have an inequality that's going to be greater than 0. Because what kind of process is this? If this is a free expansion, irreversible. Did I spell that right? Sure. So because it's irreversible, guaranteed you're going to have a positive value here, and potentially a 0. Well, because we set it up this way for free expansion, delta S of the surroundings is 0. But there is that difference between the two because of the way that you have no gain of heat energy from that type of expansion. And if you think about what kind of process this is, irreversible, spontaneous. You're going to have a spontaneous process if this is a vacuum. Okay, I hope hearing me talk out loud the nuances of this is helpful. Cool. Email if you have questions.